All right. So the final section of this chapter is about paired data. You're going to like paired data much better than you're going to like two sample data because in paired data, all we have to do is find the difference first, and then it's all one sample work again. So paired data results from recording two values of the same quantitative variable for each individual or each pair of similar individuals. So paired data implies, is there a reason for me to match individuals up? Usually paired data is data that's taken from the same individual, oftentimes before and after measurements. If we're going to kind of compare data, it doesn't make sense to compare me to you or to compare you to your friend. But it makes sense to compare you to yourself, kind of using yourself as your own control group. So when we talked about a matched pair design way back when we did sampling and experiments, that's when we would use paired data. Is there a reason to compare one individual to another? Analyzing paired data. To analyze the data, start by computing the difference for each pair. Then make a graph of the differences because we always graph the data after we first meet it. Use the mean difference, X bar, and the standard deviation difference, S of difference, as your summary statistics. So we're not going to work through this whole problem, but if you look over here, we're trying to see how fast can you do your math um, work while listening to music. Does listening to music hinder your ability to perform in mathematics? Well, it doesn't make sense to compare me doing a stats problem to you doing a stats problem because you guys are going to be way faster than I am, right? But it does make sense to compare me doing it with music to me doing it without music. Compare you with music to yourself without music. But it doesn't make sense to compare me while not listening to music and you while you are listening to music. So paired means there's a reason to compare these two data sets. So if you look here, time with music, time without music, and then down bottom, they calculated the differences. That's all you're going to do for a paired problem. Is you're going to is there a reason to compare student one to himself? Yeah, makes sense. Look at student two is slower no matter what, music or not. He's way slower than student one. So it doesn't make sense to compare student with music to number two with music to number two without music. So that's why this is a pair. Super important you can identify the paired. Okay? We subtract these values and we get this. Now it's all one sample work that we've always done before. Now it's a one sample t-test. We call it a paired t-test because first we took these two differences and paired them or subtracted them. There was a reason why I compared student one to himself because you do math at your rate. So why are we doing a paired problem? That's going to be super important for us. Now check this out. The one sample t interval, guess what? There's three conditions. Is it random? They tell us or they don't. Is the data independent? Well, is the population at least 10 times the size of the sample? Is it normal? Well, is the difference at least n greater than or equal to 30? Same exact conditions that we keep doing over and over and over and over and over again. Okay? Random, they tell us or they don't. Independence, population's 10 times the size of the sample. Normality, well, for means, normality is they tell us or central limit theorem. Okay? So check this formula out for the confidence interval. X bar, which is the difference of the two x's, plus or minus t star times the standard deviation of the difference over the sample size of the difference. Same exact formula that we used. But first, we have to subtract the two lists and use that new list to do all of our work. Other than that, it's identical to everything we did in one sample testing. Okay. So the data from the random sample of identical twins. Now, this might make sense to compare one twin to another. There's a reason to pair these problems. Yeah, that makes sense. Okay. Construct and interpret a 95% confidence interval. So I'm not going to use this data or this data. What I'm going to use is the difference between the two twins. So the data from a random sample of identical twins are shown again in the following table. construct and interpret a 95% confidence interval for the true mean difference in IQ scores among twins raised in high income and low income houses. So they took twins who were separated, right? One of them was raised by a rich family, one of them was raised by a low family. Okay. Are you smarter if you were brought up rich than if you were brought up poor? That's the question that we're trying to figure out. So the 95% confidence interval for this problem, well, it's a T problem. How many degrees of freedom does T have? Well, it's n minus 1. In this case, it's simply n minus 1, the difference. So we count here, oh, there's 12. So this problem has 11 degrees of freedom. What are we going to do? We want to construct a 95% confidence interval. A 95% confidence interval for what? The mean difference. Well, what is the mean difference? It's the true mean difference of what? High income minus low income. Of what? IQ scores for who? Identical twins. How am I going to do this? Oh, this is a one sample T interval for the mean difference. Am I allowed to do it? Random, it's a good start. Independence, are there more than 120 sets of identical twins? Yeah, we're good there. Okay. Normality, they didn't tell me n's not large enough to use the central limit theorem, so I need to make a graph of the difference. If it's roughly symmetrical, I'm fine. If there's no outliers, then I should be okay. So we can put this data into a list. So if I go to stat edit, I'm going to clear out this list from the earlier problems, and I'm going to add the data. So the first difference was 8, 5, 9, 6, 5, 8, 1, 5, 8, 1, 6, negative 1, 10, 1, and 12. Okay. Let's graph that. So go into stat plot. I only want to make one graph now because remember, paired data is nice. We can combine the two sets of data and just do one sample testing on the combined data, which makes our life a lot easier. List one, yes, graph. Oh yeah, it looks relatively symmetrical. There's no outliers or nothing strange. So absolutely, we're good for normality because it's very symmetrical looking with no outliers. Okay, so what are we going to do? We're going to estimate the true mean difference in the IQ scores for high income versus low income. Are we allowed to do it? Yeah, they told us it's random. There's more than 120, and the box plot shows that the data has no outliers or strong skewness. So we're allowed to do it. Now let's do it. Well, let's let the calculator do this one for us. So if I go to stat test, I want to do a t-test. It's not a two sample, it's just one sample because remember I combined these two samples here to make one. So it's just a straight up t-test. And yes, I have data, but it's not a test, is it? Sorry guys. We're not running a test, we're finding an interval. So I want a t interval. Stat test t interval. I'm not running a test, I'm constructing an interval. Yep, I have data. It's in list 1, and I want to be 95% confident. All right, so I have an interval of negative 0.483 to positive 21.39. All right, I'm almost done. What the heck does that mean? What did I just do? In context of the problem, what did I just find out? We are 95% confident that the interval from negative 0.483 to 21.392, wait a minute, that can't be right. Did I put the data in wrong again? There's no way the difference can be 21.39 when 12 is the greatest difference. So let me go in here, and I probably put in an extra number like I did earlier. I'm having troubles today, guys. So, yep, I put in 58 instead of a 5, then an 8. So I'm going to make that one a 5, and we'll come down to the bottom here and add the 8 in. Oops. All right, now let's try that work again. Remember, stat, test, but we're not running a test. We're running an interval, t interval, on list 1, and we want to be 95%. Calculate. That seems more reasonable. So there's no way that other answer could have been right because I couldn't have a difference of 21. Okay, so my interval goes from 3.338 to 8.3287. So I am 95% confident that twins who come from a high income family on average will have an IQ between 3.383 to 8.3287 higher than their twin who was brought up in a low income family. So does the amount of money you have when you were raised have anything to do with your IQ later in life? It appears that it does. Right? So I am 95% confident that somewhere between 3.3 and 8.3 IQ points higher for those twins who were brought up in a high income family versus those who are not brought up in a high income family. All right, so I kind of got ahead of myself there on this last one. We need to now finish this unit up by looking at a paired t-test. Okay, so this is how we do the interval. What are we going to do? Define the parameters. Are we allowed to do it? Check your conditions. Do it. Find the interval. Interpret in context. What the heck does this mean? Now we're going to run a test. Okay. So the null will always be that the mean difference equals 0. Always. The alternative could be any of the three. The alternative could be that the mean difference is less than 0, or that the mean difference is greater than 0, or that the mean difference is not equal to 0. But again, this is only a one sample test. So this is exactly the same as a one sample t-test. It's the exact same test statistic. It's the exact same conditions. The only thing different is first, you have to subtract the two lists. Other than that, it's exactly the same thing that we've been doing the whole time. Is it random? I don't know. Did they tell me? Is it independent? Well, is the population 10 times the size of the sample? Is it normal? Did they tell me? Or does a central limit theorem apply? That's it. Okay. Again, since it's a t, we need degrees of freedom. So n-1 degrees of freedom. We need a test statistic. T equals x bar, the difference of the two means after we subtract them, minus 0. Why minus 0? Because the null is always going to be 0. The standard deviation of the difference divided by the square root of n. But since the null is always going to be 0, I'm not even going to put minus 0. So my Test statistic is really just X bar of the difference divided by the standard deviation over root n. Same thing as a one sample test. So researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent. Each subject was barred from coffee, cola, or anything else with caffeine for the whole experiment. During the 2-day period, subjects took capsules containing their normal caffeine intake. During the other 2-day period, they took placebo capsules. The order in which the subjects took the caffeine and the placebo was randomized. At the end of the 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to depression. The table displays the subjects' depression scores. Higher scores show more depression. So, do the data provide convincing evidence at the alpha equals 0.05 level that caffeine withdrawals increase depression scores on average? Well, if you look at the data set, it sure looks like it, right? There was much higher depression numbers on the placebo than there was on the caffeine. Is that difference large enough to be statistically significant? That's what we're supposed to try to figure out. Okay, so how are we going to run this test? What do we want to do? Well, what is the mean difference? It's the true mean difference in depression scores of caffeine dependent people oops. What did I subtract? The mean difference of what? What minus what? So in this case, I'm going to take placebo minus caffeine. I'm going to take placebo minus the caffeine. This is a matched pair test because I'm using each individual as their own control group. Okay. Some of these people may be naturally more depressed than others. So you can't compare one person to another. That's why we need a paired test. So if I'm going to take placebo minus caffeine, this would be 11, 18, 1, 4, 6, 19, 6, 3, 13, 1, and -1. This is the data we're going to use to do all of our work. Okay? We put it in a list. We have it find X bar and S of X for us. We want to see, is the data approximately normal? Well, they tell us that it was random which day went first. So we do have random allocation in there. Did you get the placebo or the caffeine pill first? That was random. Okay. Normal? No, they don't tell us. So we need to make the graph just like we did in the previous problem. So just have it make a box plot for us and look to see if it looks roughly symmetrical. And you'll see that it does. And then independence, yeah, I'm sure there are more than 110 people who are addicted to caffeine. Now let's do it. So remember that the t-test statistic is the difference. So I put all of these in a list and I find the mean. It's 7.34. Oops, it's 7.364. 7.364 minus 0. I'm not going to write that anymore, but I will for this example. Over the standard deviation, the calculator told me that that was 6.918 divided by root 11. That gives me a T of 3.53. What about degrees of freedom? Oh, the difference -1, there's 10 degrees of freedom. So I go to table B, I look 10 degrees of freedom, and I try to find 3.53 so I can estimate my p-value. 10 degrees of freedom, 3.53 is right here. So my p-value is between 0.005 and 0.0025. So my p-value is larger than 0.0025, but smaller than 0.005. Therefore, the data is statistically significant. I would reject the null and conclude that there is a difference in depression amongst those who were given caffeine and not. So remember that the null is that the mean difference equals 0. Let me put that on the other side. Get a new color too. So remember, the null is that this mean difference is 0. There is no difference. It doesn't matter. You will not be more depressed if you're off caffeine or if you're on caffeine. Versus the alternative, what does the researcher suspect is happening? They believe that this mean difference is going to be greater than 0, that we're going to see more depression for the placebo group than the caffeine group. Since this p-value is smaller than alpha equals 0.05, the data is statistically significant. We reject the null and conclude that the mean difference is greater than 0. What does that mean? We have convincing evidence that caffeine withdrawal does increase your depression test scores on average.